other forces involved. Because the book is already moving when we come in. Subatomic particles generally come into existence already moving. The book just happened to come into existence already moving.
There's gotta be a lot of, never mind.
Just because the odds are really small for that to happen doesn't mean it can't happen.
All of bits of particles just came into being at the same time.
Right, in the exact right configuration. So, let's see, mass of the book. We'll make 4 kilograms, and mass of cup is 2 kilograms. We're going to start out with it frictionless. And what's the first thing we do? Oh, I'm going to give an angle here.
We would draw the separated diagram. Are we going through facades? Are we going through facades?
Yes.
Okay.
Now, all I really care about are the book and the cup, but for completeness at this point. Oh, and the question is, how far does the book move before stopping?
Does this sound, oh yes. What determines it stopping? Because it has this like velocity, right?
It does, but it's also going uphill and there's something dragging behind it.
Right, okay, never mind.
It will slow down. Because there's nothing propelling it up at this point, it's just already, it was already starting going that way, there's no force pushing it up.
Okay.
All right, so we separated, now what?
Now we start drawing up top, going through the forces and stuff. Just like going through the different forces, acting on everything.
Is there no ramp that the book is on?
Yeah, that's a ramp.
So why did we not include that in the force diagram? Because it's okay. I was confused.
There you go.
And is the ramp's on a table?
Sure.
Okay.
Or it's, the table has a slanted, maybe it's the side of a house, that's a roof
Right.
line. Because most modern houses have pulleys on the corner, I think.
Oh yeah.
You're telling me I've got mine since the 80s.
Darn straight.
Been using it to pull all those leaves somewhere.
And if you'd gotten it in the 70s, it would have shag carpeting on it.
Oh yeah.
Burnt sienna or lime green. All right, anyway. So, what's acting on what?
There's gravity, there's a weight
Okay.
acting on, the book and down, yeah. And then there's weight acting out on the house or whatever this is. Same thing for the cup, down on the cup, up on the earth. Assuming this is on the earth.
Sure. There's no alien world would ever do this. That's just crazy.
And that's it for gravity, cause there's no gravity acting on the rope or anything. There's normal force, acting in the up diagonal direction that way, and then opposite on the house. And then, same thing for the cup, it's acting down, no, sorry, up on the cup. Wait, no, there's no contact, never mind.
There's one other pair of normal forces. It does not have bearing on the actual solution to the problem, but
The
for
rope and the
completeness.
pulley.
Say again?
The rope and the pulley.
Yeah.
Are we assuming the pulley is part of the,
Yes.
okay. There's no other force. There's tension acting on both the cup and the book, so it's acting up on the rope, right?
Up on the rope.
No, sorry, yeah, what Ian said, so up on the cap and down on the rope. And then, up on the book, and down on the rope, or is it the opposite?
It's down on the book, well, down diagonally, and then up on the rope.
Okay,
Tension's always pulling on the rope.
yeah,
It pulls
It's
on the
always
rope.
gonna pull towards each other.
right,
No friction in this particular problem, but which way would friction be acting on what? If there were friction?
there'd be friction acting
Down and to the left on the book, and then up and to the right on the ramp.
on the,
Yeah.
yeah.
Friction's another thing that would be slowing it down. All right, so, coordinate systems. For the cup is gonna be moving upwards, the book is gonna be moving, so they're gonna be moving like this, but they're gonna be slowing down. So what exactly is the direction of acceleration of the cup?
It would be down into the, of the cup.
Okay, for the book then, for the book?
The book, sorry, the book would be down into the left in the angled ramp.
All right, so my this is not part of the force diagram. I don't know how many force diagrams I've seen where people throw acceleration into it. This is not part of the force diagram, this is just a side note. There's my acceleration that way, and for the cup,
Straight down.
Straight line.
all right. So here's a situation where the velocity and the acceleration are in opposite directions. You are going to, at this point, you make a decision. Do I want my coordinate axes, my I hat in the direction of acceleration, in which case my A will be positive, or do I make it in the direction of my velocity, in which case my A will be negative? It does not matter, just as long as you can interpret what you have in the end. Someone with an opinion, preference?
In the direction of acceleration.
All right. And we're gonna show some bold color here, so for this one, I'm gonna have acceleration this way, so I hat and J hat, and here I C.
Wait, so are we setting up two separate coordinate systems?
Yes, we are.
Okay.
This may not be that important, but I'm curious why we didn't draw a vector symbol over the side note accelerations here, when in the last problem we did. Is that because we have two of them and they're in different directions?
Yeah, that's primarily it. And, you know, A is the magnitude and the direction is represented by the arrow.
Okay.
I think putting the vector symbol over the A was,
Redundant.
yeah. All right, so now what are we bringing up? Since we did force diagram, we figured out direction of acceleration, we have the coordinate axes, decomposition.
We're gonna have to decompose the weight on the book.
Yeah. All right, so that brings us to, I have normal force acting this way, so Y sub, I think that's a B there. We have tension acting down the ramp. We'll have W sine theta acting down the ramp, W cosine theta acting into the ramp. And then for the cup, which is now looks a whole lot like a box, we still have tension acting up.
Weight acting down.
All right. And this is what I mean by we can just jump straight to sine theta's down the ramp, cosine theta's into the ramp. Because I gave the angle with respect to the horizontal. Equations of motion.
So for the positive I hat direction on the box, we have force tension plus W sine theta. It doesn't look like we're subtracting anything.
Yeah, we're not, is equal to mass times,
Acceleration,
Massive book.
massive book.
All right.
for J hat, it's, normal force of E, minus W weight cosine theta is equal to mass of book times 0?
Yep.
Okay. And then for I hat sub 2, wait, yeah, it's for the force of tension, wait, yeah, that's what FT is, right? Force of tension minus, weight of cup.
Wouldn't it be the other way around?
It's visible what you said it equal to, but we had down
Right,
being positive.
okay,
Force of
so,
tension minus
yeah,
weight of the cup.
weight of cup,
Weight-
no,
weight of cup.
weight of cup minus force of
Weight of
tension.
cup minus tension.
Yeah.
That's equal to,
Oh.
mass of the cup times acceleration.
Yeah, and it's the same magnitude as the other one.
Right.
So Henry, you were questioning something about the order here? Did it-
Yeah, I just forgot that acceleration was down.
Okay.
Yeah, same here.
Now, if you did tension minus W sub C, then that would be equal to negative
Negative.
mass times acceleration,
Right.
or mass times negative acceleration. All right, so I got my 3 equations here. This one right here, again, without friction, this J hat equation, not gonna do anything for us. So I'm basically gonna combine these two right here. Tension conveniently is positive in one and negative in the other. So I can just add the 2 equations. Add the left side, add the right sides. I do need a subscript next to this W here. Oh, substitution, let's do this in some semblance of order. The first S. For what do I have an independent formula?
Weight.
Yeah. And that's it since friction's gone. So we have tension plus MB, in subscript B, G sine theta is equal to MBA. And, sure, for completeness, Y sub B equals MBG cosine of theta. And then MCG minus tension is equal to MCA. So now we have the convenience of positive tension, negative tension. So I'm just gonna add the left sides. You get MCG minus, plus MVG sine theta is equal to MVA plus MCA.
Oh, and the tensions cancel out, cause one's
Yes.
less, okay. I was wondering why that wasn't.
You could also have solved for tension in one of the equations and plugged into the other. It adds an extra step or two. And for the camera, this is slightly off, but what I said, pretty sure I said it correctly, so just pull it from the verbal cues. I'm solving for acceleration, so I have acceleration, I need to get all my accelerations on one side, and I'm already there, and now I just factor it out. So I end up with MCG plus MVG sine theta equals MV plus MC times A. And so my acceleration, now with the formula, MCG plus MVG sine theta over MV plus MC. You could factor G out on top if you felt like it. Questions up there before we do plug and chug? Poison?
Yeah, so for I have, why did you have, why'd you have the W sine theta as a positive? Like, wouldn't that'd be negative since it's going to the left kind of?
W sine theta is acting down the ramp. And over here, we said down the ramp was the positive I hat direction.
Oh, okay. I wasn't looking at I just assumed that I hat was like that way and J hat was that way.
Oh, yeah, no,
I saw
that-
you do that, but I didn't, I didn't.
If we did that, if we had gone for the horizontal vertical on the book, then we would have ended up with that mess that we did last time for box on ramp.
Okay.
And again, if that's what you're into, I'll play some judgment, but go for it if you want to. Just remember on tests, there's other parts of the test other than that one problem. All right, any other questions, Deb?
Did you add the, add T with sin theta? Because they go same way, same
Yes.
direction?
Yeah, FT and WB sine theta are definitely in
And
the same
you
direction.
subtracted the cos one because they go opposites?
Yes.
Okay.
All right, so let's plug and chug for the acceleration of the book. Because that's all the force stuff does, is it tells us acceleration. Then we'll use that acceleration here. So acceleration, therefore magnitude of acceleration is 2 times, let's stick it on the Earth. 9.8 plus 4 times 9.8 times the sine of, is it 30 degrees? 30 degrees over 2 plus 4, which is 39.2 divided by 6. Somebody's gonna tell me what the real answer is.
No, 6.532. So 3.2 are the last two numbers, just get rid of the 7.
6.532?
Yep.
Units?
Meters per second squared?
Yeah. So is that our acceleration for the entire thing, or just one of our coordinate systems?
No, for the entire thing. Because it's an ideal route, they're gonna accelerate the same
Not the
rate.
same, yeah.
They have the same magnitude of acceleration.
And since our, oh, never mind, acceleration's down.
All right, so now we get to the linear motion problem. How far does the book go before stopping? We can change our coordinate system to up the ramp being positive if we want, or we can still make down positive. Doesn't matter. Let's just make down positive because that's where we are already. So I have displacement, which is what I'm trying to find. Initial velocity, final velocity, acceleration, and time. Initial velocity is negative 15 meters per second. And I apologize for not giving you an opportunity to say that, just to show off that you knew it would be negative.
It's a shame.
Before I said 15 meters per second, and I gave a direction up the ramp, and at this point, we define up the ramp as negative.
Our final velocity is just gonna be 0, right?
Yep. And our acceleration,
Is the 6.572. That is a 7, right?
no, that's a 3.
That's a 30, okay.
Yeah, I probably should have rewritten it. So much better, all right. Oh, by the way, our acceleration is 6.572 meters per second. There are two things that tell us that we've done something right.
I thought it was 3. Just rewrite it.
Also, I got 6.53333 repeating. Was I the only one who got that?
I got that?
I did too.
And
I think it's because you might have had it in radians, but I had mine in degrees
I think-
and
If I
Sine.
got it in
No,
radians,
that's not-
or different.
I got
It's-
6.5.
It's repeating.
Oh,
It's
yeah.
repeating.
that, being
it's,
off at this point right here would not be.
yeah, it really doesn't matter.
He
but-
didn't have an argument, so he had some leg to stand on. He did not have a leg to stand on, so he made an argument.
Sorry.
That's okay.
Yeah, anyway.
Anna shutting this stuff down.
Please.
So two things that tell us that we did something right. Number one, our acceleration, on the first part, our acceleration was positive and we expected that. We expected that acceleration to be down the ramp. 2, it is less than the acceleration due to gravity. If I threw it straight up into the air, once it leaves my hand, the acceleration is 9.8 meters per second squared down, and this is less than that because I've got more stuff involved here.
Yeah.
Although there could be a scenario, that's not necessarily a thing. So let me sort of back off on that, the second one. You can have acceleration. We could have had something greater than 9.8 meters per second squared. All right, so just rewind about a minute. Ignore the last minute.
Yeah, for the J hat, how do you have, so, we're dealing with, F equals MA, but why'd you write 0 for the second half?
Because this is the mass of the book times the acceleration in the j hat direction.
And there's no acceleration, cause it's like horizontal basically.
Acceleration is down the ramp, so perpendicular would be 0. That's the whole reason for a standard coordinate system like this, is so that one of these will be equal to 0.
But wait, so if I hat is, so in this problem, I hat is going down, right?
Yes.
Down and to the left.
Yep.
So, okay, I mean,
You
I
know
guess
how-
I can see how it's 0 if it's horizontal, but I'm trying to like, I mean, I guess it makes sense.
The box here is not, if this were not 0, that is saying that the box has acceleration in the j hat direction, which means that as it goes up the ramp, it's either cutting into the wood, or into the ramp, or it's floating off the ramp.
You know how with Fred, like when we would set up those equations, one of them would equal 0 because the acceleration, like horizontally, there's no acceleration, it's just
Yeah.
down. That's what that is.
Okay.
It's the same thing. It's just like the I hat and J hat thing.
I did have a student last year who would take, whenever he did the force diagram, he always tilted it. He tilted the problem so that, I don't know, to me, it was very confusing when I was reading his work, but it worked for him. Where he would do this, and then weight is acting, was it acting like that? So weight is acting down that direction right there, normal force that way, and
And
tension's
then
acting
working
that
that
way.
way, yeah. That's kind of what I do, but I think drawing it out would make me more confused.
Yeah, but that was his method. I mean, it's not inherently wrong, just I find it confusing. But I don't know if that image helped at all. Then,
Why is the initial velocity negative?
initial velocity of the book was 15 meters per second up the ramp. And so the magnitude is 15 meters per second, but with our coordinate system,